So I'm starting a new series regarding data structures and algorithms and how we can use them to do things with code. Uh, I think this first episode, I'm just going to go over the concept of an array. So let's look at that. Where's my mouse at? There it is. So if we insert a script here into Roblox, if you don't know how to do that, by the way, I do have a beginner series that explains all that. An array is defined like this. So we have a variable. We have local, which essentially just means the access it has to the access that is allowed for this specific variable. In this case, it's locally defined to this specific scripting environment because it's outside of any stack. The stack is another data structure that I'll get into later in the series, but it's essentially just like an array that holds things. Then we have our variable name, which is in this case it's array. Then we have a colon followed by our data type, which in this case we define it as a table because both arrays and dictionaries are tables. But in this case, we're talking about an array. Now, array is essentially just an object that holds whatever we want it to hold. And then you would have to put the type of data you're going to hold. So I'm going to put a number. Right? So the array essentially works off of numbered indexes starting at 1 to the end of the array. Python, Java, C++, I'm pretty sure every other language in existence uses the starting index of 0 for binary, like binary. But Lua decided to use 1 as the starting index. So the first index here would be 2, right? The second index would be 2, 1. Sorry, not 2. Third index would be 4. Fifth index would be 2. Sixth index would be 31. And finally, the last index in the array would, of course, be 8. So we have 31, 8. All right. Now, let's look at what this looks like in detail. So, say we're given array A. And yes, my handwriting is horrible, so you guys are probably going to get used to it. That's why I use a computer to type. I don't ever use my handwriting. We're going to put 4 letters in. 8, 3, 6, and 2. Now, these don't have to be letters. They could be strings, objects. It could be whatever you want. But in this case, for simplicity, we're going to use numbers. So this little array here holds 4 items. So it has the first index is 1, second index is 2, third index is 3, fourth index is 4. Now, we're going to talk about how they work in memory. How arrays work in memory is actually quite interesting. Essentially, they occupy their own individual block that it can dynamically expand depending on the type of object that you're using. For instance, Java has something called array lists, which are dynamically resizing arrays, or dynamic meaning constantly changing in size. Now, in this situation, we actually have Lua gives us dynamic arrays. We don't have to worry about them resizing because it does it for us, so we don't have to worry about the memory management. However, in a lower level language like C++, you would want to worry about the you would want to worry about dynamically resizing them. And how do you do that? Because arrays in C++ are statically typed. Once you give it a size of the array, you can't change it unless you make a new block in memory with that size. And that's when you use vectors. Vectors are the array list in Java. Okay, so why did I tell you that? Well, we can actually calculate for the end memory address in this array. So let's say your starting address I spelled address wrong. Still pretty sure I spelled it wrong. Let's say our starting memory address for this index here, index 1, is 0x0062. It wouldn't be 62 unless we had, or to do 64. So the data type size of an integer is between 4 and 8 bytes, because that's just the data type size of that specific object. Because where we can hold now a character, however, a singular character in another low-level language like Java or C++, they're actually 1 byte because it's a number range between 0 to 255. However, Lua doesn't classify them as that. They classify them as numbers, so they would actually take up 4 to 8 bytes in memory, depending on the size. Now, let's look at this. We have first index, which of course we have our starting memory address. We can actually solve for the second index by doing a simple formula. The formula for that is the index we're on plus essentially the multiplication of the data type value and it's the starting index. So the starting index, yeah, I was right. Why did I erase that? It's the starting index, so the start address, plus the multiplication of the size of the data structure or the data type times the index of the array that we're at, so I. Now what this will do is it'll give us the memory address relative to the first address here. That is a horrible circle. So if we wanted to calculate the second index, well, this is important to note. We can't actually use these numbers. We'd actually have to shift the whole array down by 1. So we'd have to subtract 1 from each of these to calculate, because we have to start at 0. It'd actually give an incorrect value because arrays actually start at 0. So in the case of Lua, we'd have to do start plus the size times the index minus 1. And that will be our new value. So in the case of this, let's say we have this number, 0x064. Well, let's do some math. 0064 plus the size, which is 4 bytes, minus 1, or times 1. And that will give us our new memory address for the second index. So let's see, 64 plus 4 times 1, 68. So this would be our new memory address for this second index. Now, why am I telling you this? Well, now we can understand how arrays work. The reason that arrays can use numerical indexes is because they are directly next to each other in memory. We can go array 1 in Lua, not other languages, array 1 to get the first index. We can do array 2 to get the second index here, which is 3. We can do array 6 to get the third index, or we don't have 6 items in the array. Array 6 to get a nil value, because array 6 doesn't exist. Now, if you did this in any other language, without it being dynamically typed, it would actually error. But since we are automatically have a resized array, it'll just return nil, like it doesn't exist. And then A3 to get 6. So that's essentially how arrays work in memory, right? So the reason that arrays are fast for certain operations, if we want to look at the exact operation notation of that, I can copy this little time complexity chart here because I don't feel like writing it down. This is what I use to memorize it. We have retrieve index, O1 constant time. That's his big O notation. I should probably tell y'all what that is. Give me a second. Big O is a concept of notating and analyzing algorithmic time and space complexities. That's essentially the way that we determine how fast code is. So big O notation is usually, here's an example of the big O notation. O of 1 is ideal. That means it's just a straight line. We don't have to worry about it. O log of n is, that's pretty good. There's a lot of binary search trees are actually O log of n. So that's something that's useful to search if the search tree is binary search tree is balanced. If it's not balanced, then it'll be O of n linear time because it's basically a linked list, which I'll get into later. Then we have n here, so O of n. That is our O of n. I forgot what that symbol is called, but y'all know what I mean. That is also an ideal time complexity and space complexity. Then we have O of n. This is basically whenever you insert a loop, it'll be O of n, right? Whenever you're looping through something, whenever you're doing anything regarding finding something in an array or finding something in a dictionary that you don't know exists, that is O of n time. That is, as you can see, it scales exponentially. Then n log of n is, you'll never, yeah, we don't talk about that because that's horrible. Then we have n squared. That is, oh man, that is not ideal at all. Then we have 2 to the power of n. That is also extremely not ideal. Then we have n factorial, which basically never ends your program. So it never reaches 0. Meaning it will constantly stall your program the entire duration of it running. So as we can see, let me use a pencil. So as we can see, we have retrieve index is a constant time of 1. Meaning if we know the index, we can just do this, and this is O1 time complexity. Now then we have retrieve an index. This is linear because we actually have to loop through the array. We have to go 1 to 2 to 3 to 4 to find the item. And if it doesn't exist, we either return its index, or if it does exist, we return its index, or we return nil, which is what we did here with O of 6. We know the 6 index doesn't exist, so we can just automatically return nil because we assume it doesn't exist because we check the array. Now we have this index here, 3. Well, we know 3 exists because it's 6. But we had to look for that if we didn't have the index. We couldn't just randomly know that this is a 3 without us knowing to iterate through it. That's why you can find many developers combining multiple different data structures together to essentially speed up this process. So then we want to add an element, has a to the end of the array. Notice this word end. If you add it to the end of the array, it'll actually be of O1 space complexity, right? Now, if you want to add an element to a full array at the very beginning, it has to shift everything over in memory. So if I add an item here, it'll have to shift over everything else because that is no longer the starting array or starting memory address of the index or the array. It has a new value there that is relative to that. So we'd have to shift everything from the beginning on over, which is O of n time complexity because it's a big shift. For instance, if I were to put 3 here, I'd have to shift 8 over, 3 over, then 2 over. Now insert or update an element at a specific index. This is O1 because we can index this like this array. Let's say we wanted to go, since we added 3, we now have 5 indexes. 5 indexes. The 5th index is 2. So if I wanted to change the 5th index to 1, I could do that. Now this is no longer 2, it's actually 1, right? Let me get a bigger eraser. So O of this is 1 now, because this is the 5th index, right? Now, we have delete an element by setting it to null. That's exactly what we can do here. We can also set, instead of 1, we can do null. Now it doesn't exist. Now our array size would actually be 4 again, right? So the first index would be 3 here, second index would be 8, third index would be 3, fourth index would be 6. So our first index here is 3, second index, of course, is 2, right? Because we start here. We could also, to make this neater, we could shift it over, but we're about done with this list, so there's no point. But if it's confusing, just DM me on Discord. Delete an element to, yeah, we already did that, and delete an element by shifting the elements. This is, of course, O of n. For instance, if we wanted to delete an item at the end of the array, we would actually have no time complexity issue, right? Because we would just delete it and set it to nil, right? Set it at the end to nil. Well, that gets a little more complicated if you want to have an array without spaces. If you were to delete something in the middle of the array, ideally you would want to shift over every item that is before that or after that index. So if I was to remove 3 here at the third index, I would want to actually shift over everything past on this side from the everything on the right into the left. So it's actually, there's no spaces or gaps in that array. And that's O of n complexity, of course, because you're iterating for each item. And that's arrays. I mean, yeah. In Lua, they're pretty simple. You know, if you wanted to print out an item, you can do array1, print out the first index, or you can print out array hashtag array. This will get the size of the array. This will print out the last item. And yeah, that's arrays and how they work in memory and how they function. Have a great day.